Amateur radio is a wonderful hobby in which licensed radio amateurs across the world communicate with each other using two-way radios. For becoming a licensed radio amateur, you need a license from the regulatory authority in your country. In India, the regulatory authority is Wireless Planning and Coordination Wing of the Department of Telecommunications under the Ministry of Communications, Government of India. Regular examinations are conducted and you have to qualify the examination as well as get a license from the WPC before you start operating an amateur radio equipment. Amateur radio equipment are of various types. There are simple handheld walkie-talkies which allow for a short distance communications, and with the same walkie-talkie, if you have a directional antenna, you can point your signals to satellites like International Space Station going above your head at specified timings, and signals go from the walkie-talkie to the International Space Station and down to the Earth another location, and you can communicate between radio amateurs using amateur radio satellites. Typical example is communication through the International Space Station. I also participate in that, and I'm very happy to communicate with my friends using amateur radio on International Space Station. Then there is something known as shortwave radio or high frequency HF radio. Communication through International Space Station is using VHF, very high frequency and ultra high frequency radios, which could be handheld radios or base stations at your home, which need external antenna. In case of shortwave communication, you have the radio at home and the antenna is outside, and the antenna sends signals to the ionosphere of the Earth, that is a layer of the atmosphere with ionized particles, ionization depending on the solar activity. So it will send signals to the ionosphere and bounce off the ionosphere to the Earth, and then from the Earth again to the ionosphere, and multiple bounces will take you, or rather your signal, across the world to the other side also. For example, I can communicate from my home to a station in United States of America using shortwave or high frequency radio. Now, what is the role of amateur radio in this era of internet and advanced telecommunications? You can easily communicate with your mobile phone as well. This is a hobby which has been there for over a century, and the importance comes that it is an experimentation hobby. That is, you can advance your technical knowledge, you can make your own radio and communicate, you can make your own antenna systems and communicate, as well as learn a lot of this technology of communication. That is not all in amateur radio. There is a more noble cause in amateur radio. Whenever there is a natural calamity, the communication infrastructure in the region can sometimes crumble. Mobile phone networks can go, electrical power can go, and you may have a situation where the only mode of communication which is possible is amateur radio. This has occurred several times globally. During such major calamities, natural calamities, when infrastructure for communication may not be working, amateur radio operators often provide volunteer service to the community in the form of emergency communication. During the recent Wayanad landslide disaster, several radio amateurs provided volunteer service in the region. One of my friends was called upon by the district administration to provide a vital communication link between the district headquarters and ground zero, where there were no communications tower at that moment. After a few days, communication towers were established, and then the role of amateur radio operators was only standby support. But in the early hours after the disaster, our own radio amateurs in this region could provide vital communication link using handheld and base stations between the ground zero and the office of the district administration. That is an important role of amateur radio even in this era of so much technological advancements. In India, any person above the age of 12 years can appear for the examination known as ASOC examination, Amateur Station Certificate Operators Examination. Indian citizens between 12 to 18 years need an undertaking by their parent or guardian to appear for the examination, while those above 18 years need not have this undertaking. They can directly appear on their own for the examination. There are two grades of examinations. One is restricted grade with lesser privileges and lesser power output of the radio, while general grade provides all the facilities provided for radio amateurs in India. These examinations are conducted at wireless monitoring centers across the country. In Kerala, we have one at Thiruvananthapuram, and in Karnataka, there is one at Mangalore, and there are several other monitoring stations across the country. There are also international monitoring stations where you can appear for the examination. But you have to be a citizen of India to appear for this examination for license in India. Now, there are two examinations for restricted grade and general grade. And for restricted grade, there are two papers. One is Section A, Basic Electronics, and Section B, Radio Regulations. While for restricted grade, you have to appear for an examination of 1 hour duration each with 25 questions. In general grade, there are 50 questions and the examination duration is 2 hours. You can appear for both examinations together as well. The fees is only just 100 rupees, and if you apply for both exams together, you can appear with just 200 rupees. So fees is very nominal. For restricted grade, you have to get 40% mark in each section and 50% in aggregate. While for general grade, you have to get 50% in each section and 60% in aggregate. That is how you qualify for the examination. For general grade, in addition, you have to qualify a Morse test, that is a telegraphy-like test, Morse code, which is international Morse code, which we all sometimes use for communication. And currently you need that, but the regulation might be revised. And whenever you are applying for the examinations, you have to visit the Saral Sanjar portal. That is the place where you apply online for the examination. And when you pass the examination for the license, Saral Sanjar portal of the Department of Telecommunications. So whenever you apply, you have to look at the current regulations at the time of examination, not what I am saying now. Then there is an exemption from appearing for Part A or Section A of the examination, Basic Electronics, for those who already possess a technical qualification, either an engineering degree in the field of electronics and communications or a diploma. You are exempted from appearing for the Part A of the examination. Obviously, you don't need to learn that. You already know that. And it will be very easy for you to appear for that examination if you already have a qualification. But you are exempted from appearing for Part A. You need to appear only for the Part B of the examination, Radio Regulations. There are so many technical students in our country, so that anyone can apply after they pass the regular examination. And we have thousands of radio amateurs in our country, while some of the countries have several hundred thousands of radio amateurs. So it's an exciting world awaiting you once you pass the examination and get the license. Now, if you are residing in a city where there is no wireless monitoring center, there is also a facility for conducting an examination in your own city. In fact, we had conducted one in our educational institution long back. So if you have at least 20 candidates, you can request for an examination to be conducted at that center, which should be an educational institution or an amateur radio club or society. So we can have that facility, but it needs advance intimation and permission from the WPC. So that is also possible. Many of the places it is also being carried out, but that is not routine. Routine is you have to go to the monitoring station and appear for the examination there, and after qualifying the examination, when the results come, you have to apply for the license. So in this series, we'll go through how to prepare for the examination a little more in detail on a regular basis, so that we can have many more radio amateurs on the air. To start with, we will go through the list of topics to be learned while appearing for the Amateur Radio License Examination ASOC in India. Most of you will find that many of the topics in basic electronics for part A of the exam have already been learned at the basic level at school science classes. We will have to refresh our memories as well as learn a bit more. Radio regulations in part B of the exam have to be learned in full, as that is what we have to follow as an amateur radio operator. First, we will have a look at the topics for restricted grade examination and then see what are the additional topics to be learned for a general grade examination. As mentioned previously, we can appear for both exams simultaneously by paying the fees for both examinations, so that if we pass at least the restricted level, that level of license will be granted in due course. Once you start working as an amateur radio operator, it is easier to learn further and clear the next level. List is for general information while preparing for the exam. Check the updated syllabus from the examination center before appearing for the examination, as details might change over time. New regulations may come into force as well. Elementary electricity and magnetism. Elementary theory of electricity. Passive devices like resistors, inductors, transformers, capacitors, and active devices, diodes, transistors. These all can be combined together in integrated circuits. Kirchhoff's current and voltage laws, simple applications of the law. Conductors and insulators, properties, units of circuit elements, Ohm's law. Conductance, definition of self and mutual inductance. Power and energy, definition, units and symbol applications. Permanent magnets and electromagnets, definition, properties and their use. Elementary theory of alternating currents. Sinusoidal alternating quantities, definition of peak, instantaneous, RMS, that is root mean square, average values and its symbol application. We know that usual alternating current is a sinusoidal current which you are getting in the main supply, and all your radio transmissions generate sinusoidal alternating currents but at higher frequency. Phase, reactance, impedance, power factor, definition, units and symbol applications. Parallel and series circuits, series and parallel circuits containing resistance, inductance, capacitance. Resonance in series and parallel circuits, coupled circuits. Rectifiers, voltage regulation and smoothing circuits, their basic knowledge and symbol applications. All these will be useful if you are homebrewing radio equipment. Elementary theory of semiconductor devices, diodes and transistors. Properties, use of these devices for construction of amplifiers, oscillators, detectors, and frequency changers. Radio receivers, principles and operation of TRF, tuned radio frequency, and super heterodyne receivers. Now, modern commercial receivers are mostly software defined radios, much more advanced than these simple circuits. CW, continuous wave reception, that is Morse code. Receiver characteristics like sensitivity, selectivity, fidelity, adjacent channel, and image interference. Image interference is for super heterodyne receivers. AVC, automatic volume control, and squelch circuits, signal to noise ratio. Squelch is silencing of baseline hissing noise in FM radios. Transmitter, principles and operation of low power transmitter. Crystal oscillators. Crystals are used to stabilize the frequency of oscillators. Stability of oscillators. Basic knowledge about construction of semiconductor based transmitters. Radio wave propagation. Basic knowledge of electromagnetic spectrum. We use only a small portion of the electromagnetic spectrum, that is the radio waves. Wavelength, frequency, frequency bands, nature and propagation of radio waves, ground and sky waves, space waves, skip distance, skip zone, and fading. Most of this I have covered in videos in my previous sections. Aerials, common types of transmitting and receiving aerials. We call these antennas. Frequency measurement, measurement of frequency and use of simple frequency meters. Most of the modern radios have built-in frequency measurement devices. Section B, radio regulations. New regulations may come into force as well, so please check. Knowledge of Indian Wireless Telegraph Rules 1973, Indian Wireless Telegraph's Amateur Service Rules 1978 and amendments. Knowledge of ITU, International Telecommunication Union, radio regulations as relating to the operation of amateur stations, with particular emphasis on the following as per provision of Radio Regulation 2008 edition. This also might get updated later. Designation of emission in Appendix 1. Phonetic alphabets and figure code, Appendix 14. Nomenclature of the frequency and wavelength, Article 2. Frequency allocation for amateur services, Article 5. Interference measures against interference and tests, Article 15. Identification of stations, Article 19. Distress signal, call and message transmissions, Article 30, 31, 32 and 33. Urgency signal, call and message transmissions, Article 30, 31, 32 and 33. Amateur station, Article 25. Call sign series allocated to India, Appendix 42. Standard frequency and time signal services in the world. The following Q codes and abbreviations shall have the same meaning as assigned to them in the convention. QRA, QRG, QRH, QRI, QRK, QRL, QRM, QRN, QRO, QRS, QRT, QRU, QRV, QRW, QRX, QRZ, QSA, QSB, QSL, QSO, QSU, QSV, QSW, QSX, QSY, QSZ, QTC, QTH, QTR and QUM. Abbreviations: AA, AS, AR, AS, C, CFM, CL, CQ, DE, K, NIL, OK, R, TU, VA, WA, WB. These abbreviations are mostly used in CW or Morse code transmissions. In addition to the topics for restricted grade examination, the following items must be learned for the general grade examination. Principles of communications. Elementary idea of analog and digital communication. Need for modulation. Amplitude, frequency and pulse modulation. Elementary idea about demodulation. Alternating current. Basic concepts on construction of transformers. Definition of transformer losses. Transformer as a matching device. Semiconductor devices and transistors. Elementary principles of conduction and construction. Symbols and biasing methods. Power supplies. Basic knowledge of half-wave and full-wave rectifiers. Definition and application of bridge rectifier, smoothing and regulating circuits. Transmitters and receivers. Elementary principles of transmission and reception of facsimile and television signals. Propagation. Characteristics of ionosphere and troposphere. Properties of ionosphere layers. Critical frequency and day and night frequencies. All these are important when you operate amateur radio stations, especially on the HF bands. Aerials. Principles of radiation. Aerials for different frequency bands, including aerials for microwave, though we do not often operate on microwave ranges. Space communications. Elementary principles of communication via satellites. Specialty for general grade is that you need Morse code, both sending and receiving at 8 words per minute. Morse code is not mandatory in many countries, so this regulation also might change in future. Which layer of ionosphere disappears during night time? A. F, B. E, C. D, D. C. These are the layers of ionosphere within the atmosphere by daytime and nighttime. Lowermost is the D layer. D layer is the one which absorbs medium waves, so that medium waves will not get reflected by the ionosphere during daytime, and propagation is by ground wave propagation. But at night, what happens is that the D layer disappears due to decreased ionization. Then medium waves can penetrate up to the E layer and get reflected. That is why medium wave stations can be heard at a longer distance during night. E layer is the one which reflects the short waves usually, because short waves will not be absorbed by the D layer and they will be reflected by the E layer. Still higher frequencies in the shortwave range will go beyond the E layer and get reflected from the F1 or F2 layer. The difference between F1 and F2 is that when there is higher ionization during daytime, F layer splits into two, F1 and F2. At night, when the ionization decreases, these two layers fuse together and there is only one F layer at night. Long distance amateur radio communication depends mainly on short waves reflected by the ionosphere. Line of sight propagation is the mode of communication in A. Low frequency, B. High frequency, C. Medium frequency, D. Very high frequency. Low frequency or LF band is from 30 to 300 kHz. Medium frequency or MF band is from 300 kHz to 3 MHz. High frequency or HF band is from 3 to 30 MHz. Very high frequency or VHF band is from 30 to 300 MHz. Higher bands like VHF, UHF and above have line of sight propagation, meaning that it will not be heard beyond the horizon where the Earth's curvature sends the signal off to space. But there is some difference between actual radio horizon and visual horizon. Usually, radio horizon is a bit beyond the visual horizon. In lower bands like LF and MF, ground wave propagation while waves bouncing off the ground can take signals beyond the horizon. In case of HF band, reflection from the ionosphere can take signals very far around the globe. VHF and UHF penetrates the ionosphere and goes into outer space without getting reflected from the ionosphere. That is why only line of sight communication is possible without the aid of a repeater or satellite. Long distance communication through satellites is possible with VHF and UHF as the satellite receives the uplink signals from Earth and retransmits back to Earth on different frequency known as downlink. Which of the following is an advantage of a Class C amplifier? A. High efficiency. B. Linear operation. C. No need for tuned circuits. D. All of these answers are correct. Conduction angle of Class C amplifier is less than 180 degrees, meaning that less than half of the input signal is used. This leads to high distortion and requires a tuned circuit as load. It is suitable for radio frequency transmitters operating at a single fixed frequency. Efficiency is as high as 80% in such radio frequency applications. Diagram shows the output waveform in the absence of a tuned circuit. When a tuned circuit is used in the output, it restores the waveform to its proper shape. The resistor shown in the diagram is replaced by a parallel tuned inductor-capacitor combination which resonates at the operating frequency. Power transfer from the inductor can be done using a secondary coil wound on the inductor. Average voltage at the collector is equal to the supply voltage, and variation in signal voltage can be between 0 and twice the supply voltage during the radio frequency signal cycle. Bias voltage of the transistor is adjusted so that it conducts only for about 1/3 of the radio frequency cycle, 120 degrees or less. Another session of ham radio exam preparation is here with multiple choice questions followed by discussion with illustrations. The transformer works on the principle of A. Self-inductance, B. Mutual inductance, C. Both A and B, D. None. Transformer works on the principle of mutual inductance for transforming voltage, current and impedance. It has a primary and a secondary coil with magnetic flux linkage. Alternating current passing through one coil induces a current in the other coil. The two coils can be wound one on top of the other or on two limbs of a continuous magnetic core, typically a laminated one, to prevent eddy currents. Alternate option is a toroidal transformer wound on a ferrite toroid. Voltage in the secondary winding is related to that in the primary winding according to the ratio of number of turns on both sides. If the primary winding has more turns than the secondary winding, it acts as a step-down transformer and vice versa. Here is a step-down transformer used in linear power supplies with outer cover removed to show the laminated core inside. Circuit mounted on the breadboard is a bridge rectifier along with a high-value filter capacitor to smooth out the ripples in the rectified direct current. This picture shows different types of inductors which work on the principle of self-inductance. Couple of them are wound on toroidal cores while another is wound on a ferrite rod. Inductors are used in tuned circuits and band pass filters in radios. The frequency of oscillation of a series resonant circuit is A f equal to 1 by 2 pi into root of LC, B f is equal to 1 by pi into root of LC, C f equal to 2 pi into root of LC, D none of the above. When an inductor and a capacitor are connected in series, the reactance of the inductance tends to cancel the capacitive reactance. So the total reactance will be the difference between the inductive and capacitive reactances. Reactance of the inductor is directly proportional to the frequency, while that of capacitor is inversely proportional. For every combination of inductor and capacitor, there will be a frequency at which inductive reactance will fully cancel the capacitive reactance. That will be the resonant frequency of the combination. If the resistance in the circuit is negligibly low, then current can go very high at resonant frequency. Resonance for a particular frequency can be achieved by varying the capacitance of a variable capacitor to match the reactive inductance of a coil for the frequency to be received. At resonance, inductive reactance 2 pi FL is equal to 1 by 2 pi FC, the capacitive reactance, where F is frequency, L the inductance, and C the capacitance. In a series resonant circuit, the impedance is lowest at the resonant frequency. Frequencies quite away from the resonant frequency have a high impedance and will not pass through a series resonant circuit. Resonant circuits are used in frequency filters. Series resonant circuit allows the resonant frequency to pass through, while a parallel resonant circuit blocks the resonant frequency. The capacitor is a passive device, B active device, C both A and B, D none of the above. Passive devices are electronic components like resistors, inductors, transformers, and capacitors. They do not alter the waveform of an alternating current applied to them and hence cannot be used to amplify or rectify currents. Passive electronic components do not require an external power source and can store, dissipate, or consume energy in a circuit. Active devices are vacuum tubes, semiconductor diodes, and transistors, or a combination of active devices and passive devices like integrated circuits, which require an external power source. They can change the waveform of an alternating current applied to them and hence can be used for amplification and rectification. They can also generate signals. Bridge rectifier is A. full wave rectifier, B. half wave rectifier, C. both A and B, D. none of the above. Bridge rectifier is a full wave rectifier which uses 4 diodes instead of 2 in the usual full wave rectifier and 1 diode in a half wave rectifier. The full wave rectifier utilizes both halves of the input alternating current cycle, unlike half-wave rectifier which utilizes only one half cycle. The image shows a step-down transformer, schematic of a bridge rectifier, and 4 diodes mounted as a bridge along with a filter capacitor on the breadboard. In the process of modulation in a radio communication system, A. Signal frequency is more than carrier frequency. B. Signal frequency is less than carrier frequency. C. Signal frequency will be directly transmitted. D. Signal frequency equals carrier frequency. In a typical radio communication system, the carrier frequency is the radio frequency range, which is much higher than the signal in the audio frequency range. Human voice has a frequency in the range of 20 Hz to 20 kHz. Most amateur radio signals have frequency in megahertz range, like 3.5 MHz for 80 meter band, 7 MHz for 40 meter band, and 14 MHz for 20 meter band. VHF or very high frequency amateur radio band uses frequencies in the range of 144 to 146 MHz in India. All these are much higher than the audio frequency range. This is an animated diagram illustrating the difference between radio waves modulated by amplitude modulation and by frequency modulation. The vertical axis represents the amplitude, either voltage or current, of the signals, and the horizontal axis represents time. The top graph is labeled signal is the modulation signal, voice signal in case of usual radio transmissions, applied to the transmitter in this simple example of a sinusoidal wave. Actual audio from a human voice will have multiple frequencies. Only the extremely low frequency ELF electromagnetic waves used for submarine communication comes in the range comparable to audio frequency. But they do not send voice modulated signals. Instead, they use a form of frequency shift keying to transmit information at very low speeds. The output signal of a common emitter amplifier will be A. 45 degree out of phase, B. 90 degree out of phase, C. 180 degrees out of phase, D. 270 degrees out of phase. Most common type is common emitter configuration, in which emitter is grounded, base acts as the input and collector as the output. So the input is given between the base and the emitter, which is grounded. Current gain in this configuration, which is the ratio of collector current to the base current, is known as beta or HFE, which stands for hybrid parameter forward current gain common emitter. Beta is always more than 1. This configuration has medium input and output impedance levels. Both current and voltage gains are medium. There is a 180 degree phase change between input and output, so that output is the inverse of the input. An oscillator is based on A. Positive feedback, B. Negative feedback, C. No feedback, D. Both A and B. Oscillator in electronics is a circuit which produces periodic oscillations or alternating signal, which could be a sine wave, square wave, or another type of wave. The oscillator is powered by a direct current source and can be used in a wide variety of applications like radio, television, computer, and mobile phone. In the animation, a resistor capacitor RC network is used to feed a portion of the output of the inverting Schmitt trigger into its input. Schmitt trigger is a circuit with hysteresis implemented by applying positive feedback to the non-inverting input of a differential amplifier. It is called a trigger because the output retains its value till the input changes sufficiently to trigger a change. That brings us to the most common form of linear oscillator or harmonic oscillator, in which a transistor or operational amplifier is connected in a feedback loop with output fed back into its input through a frequency selective electronic filter to provide positive feedback. In the illustration, the RC network does this job. The output signal of a detector in a communication receiver is in A. Audio frequency range, B. Radio frequency range, C. Intermediate frequency range, D. None of the above. Typically, detection is the process of extracting the modulating signal from the radio frequency signal received by the radio. So, output signal will be in the audio frequency range. Intermediate frequency is the output of the mixer which mixes the received signal in a super heterodyne receiver with a local oscillator signal. In double conversion receivers, there will be two intermediate frequencies, while in the direct conversion receiver, there is no intermediate frequency. That is because local oscillator frequency in a direct conversion receiver is at or very near that of the received radio frequency signal. The following type of oscillator will be more stable: A. RC oscillator, B. Hartley oscillator, C. Colpitts oscillator, D. Crystal oscillator. Crystal oscillators are more stable than other types of oscillators, but the disadvantage is that they can operate only on a fixed frequency. Even frequency of crystals can drift with change in temperature, as the quartz crystal can expand or contract. That is why in high precision equipment, crystal temperature is controlled, typically in a warm chamber known as crystal oven. Then they are called oven controlled crystal oscillator, OCXO. Other methods of stabilization are with analog circuits to compensate drift in frequency with temperature, known as TXCO or temperature compensated crystal oscillator, and microcontroller compensation, known as MCXO. For a step down transformer, the relation between the number of turns in primary NP and the number of turns in secondary NS is A. NP more than NS, B. NS more than NP, C. NS equal to NP, D. None of the above. For a step down transformer, the number of turns in the primary winding is higher. In case of step up transformer, secondary winding has more number of turns. The turns ratio between the primary and secondary windings gives the ratio between the primary and secondary voltages. Welcome to the fourth session on ham radio exam preparation. YouTube has enabled auto dubbing on this channel. So sometimes you may be hearing me in your own language. If that is so, you can see auto dubbed mentioned below the title of the video. You can enable and disable auto dubbing feature by going to the settings icon of the YouTube player. So I hope that it will be possible for other language users also to understand the video. There might be some minor errors in translation because it is an automatic translation done by YouTube and may not be as accurate as what I am telling. Anyway, overall it may be good. I have tested in some of the languages which I know, that is my own mother tongue Malayalam, and also in Hindi a little bit. Other languages I will not be able to say because I am not familiar with most of the other global languages. So have a nice time, prepare well for the examination, and come on air after getting your license, and I'll be very happy to work you on air after you have studied my classes. What is the power of a device running at a voltage of 13.8 volts DC using a current of 10 amperes? A 138 watts, B 0.7 watts, C 23.8 watts, D 3.8 watts. In DC circuits, power is the product of voltage or potential difference and the current flowing through the circuit. In case of alternating current circuit, difference will be there depending on whether the load is purely resistive or having a reactive component like capacitance or inductance. That is because when there is a reactive component in the circuit, current and voltage are not in phase, meaning that they do not rise or fall in the same pattern. Capacitance blocks direct current once the capacitor is charged. Inductance opposes the rise in current in the initial phase after the circuit is switched on. In AC circuits, power consumed by a device may not be equal to the product of current and voltage across it. For example, if a transformer is connected to an AC voltage and the output is connected to a load, power consumed by the transformer will be usually very low compared to that consumed by the load. What type of capacitor is often used in power supply circuits to filter the rectified AC? A. Ceramic, B. Tantalum, C. Mica, D. Electrolytic. Filtration of ripples in the rectified direct current output of rectifiers need high value capacitors, typically 1000, 2000 or more microfarad electrolytic capacitors. Larger the value of capacitor, better the smoothing effect of the waveform to near perfect DC level. If filtering is not good, it will produce a hum in audio amplifier circuits. Frequency of hum will depend on the frequency of the alternating current and the type of rectifier circuit used. Half-wave rectifier produces a hum at the frequency of the input AC, while full-wave rectifier produces a hum at double the frequency. In addition to capacitors, high-value inductors may also be used in power supplies to give better filtering of AC ripples. The core of power supply transformer is laminated to A. Decrease impedance, B. Increase impedance, C. Decrease eddy current losses, D. None of these. I have just removed part of the cover of the transformer just to show the laminated core. You can see that this core is made of several laminated sheets, and the lamination is needed to prevent eddy currents. The core will have eddy currents, will heat up the core, and that can be prevented by using a laminated core. And when eddy currents are there, that will cause generation of heat and loss of energy, so that the efficiency of the transformer in converting the power will be reduced if you use core without lamination. Core with lamination will improve the efficiency of the transformer. When frequency of a carrier is varied according to modulation, the result is A. Frequency modulation, B. Amplitude modulation, C. Product detection, D. None of these. Here is an animated diagram from Wikipedia illustrating the difference between radio waves modulated by amplitude modulation and by frequency modulation. Vertical axis represents the amplitude of the signal, which could be voltage or current. Horizontal axis is time. Top graph is the modulating signal, a simple sine wave in this case. For audio signal, there will be multiple such waves at different frequencies in the audio frequency range. Middle graph shows amplitude modulation, in which amplitude of the radio frequency wave changes according to the signal frequency. In the last tracing, The frequency of the radio wave varies according to the modulating signal in frequency modulation. Handheld radios in VHF-UHF range usually use frequency modulation. Amplitude modulation is the usual mode used by broadcast stations. Amateur radio HF transceivers usually use amplitude modulation and then filter out the carrier and one sideband to produce single sideband or SSP signals. Which among the following is not a directional antenna? A. Whip antenna, B. Yagi-Uda antenna, C. Loop antenna, D. Dish antenna. Whip antenna is an omnidirectional antenna which radiates all around. Yagi-Uda antenna radiates towards the direction of the directors. Loop antenna has maximum signals along the plane of the loop and a null perpendicular to it. Dish antenna radiates and receives in the direction of its focal point. Now let us practice some multiple choice questions on resistors based on previous discussion. Which among the following materials have poor conductivity? A. Copper, B. Aluminum, C. Ceramic, D. Silver. Correct answer C. Ceramic. All others are metals which in general have good conductivity and low resistance. Conductivity depends on the availability of free valence electrons in atoms with incomplete filling of the outer shell. The unit of resistance is A. Mho, B. Volt, C. Ampere, D. Ohm. Correct answer D. Ohm. Mho is the unit of conductance, which is the inverse of resistance. Volt is the unit of voltage or potential difference. Ampere is the unit of current. A resistor with red, violet, orange, silver bands has a value of A. 27 kilo ohms plus minus 10%, B. 23 kilo ohms plus minus 5%, C. 27 kilo ohms plus minus 5%, D. 2.3 kilo ohms plus minus 10%. Correct answer A. 27 kilo ohms plus minus 10%. Red has a value of 2 and violet a value of 7. Third multiplier orange color has a value of 3. So 27 is multiplied by 10 to the power of 3 or 1000 to get 27 kilo ohms value. Fourth band of silver color indicates 10% tolerance or variability from the color coded value. Which digit does the color yellow denote on a resistor color band? A. 3, B. 2, C. 4, D. 7. Correct answer C. 4. Color denoting a value of 3 is orange, that denoting 2 is red, and that for 7 is violet. How many connections does a potentiometer have? A. 1, B. 2, C. 3, D. 4. Correct answer C. 3. Potentiometers are variable resistors and they have 3 terminals, unlike the usual resistors which have only 2 terminals. Central terminal provides the variable resistance with respect to the other terminals. Potentiometers can have a turning knob to alter the resistance value in the circuit and are widely used as volume controls in radios and amplifiers. A preset potentiometer is one in which the resistance value can be changed using a screw mechanism and set at the value until it is altered later if needed. What is the effective resistance when two 10 kilo ohms resistors are connected in parallel. A 20 kilo ohms, B 5 kilo ohms, C 15 kilo ohms, D 100 kilo ohms. Correct answer 5 kilo ohms. When resistors are connected in series, the total value is the sum of the two values. But it is not that simple when you connect resistors in parallel. You must take the inverse value of each resistor, sum them up, and finally get the inverse of the sum to get the final value of resistors connected in parallel. Here is a demo of checking the total resistance value when two 10 kilo ohm resistors are connected in series. Total value displayed is 19.24 kilo ohms. The selector of the multimeter is in the 20K range. The value is within the 5% tolerance or variability range of a resistor with a golden tolerance band. Here the two resistors have been connected in parallel and the value displayed is 4.87 kilo ohms, which is also within 5% of the variability or tolerance limit. When the exact value of the resistor needed for a circuit is not available, you could also use these methods of combining two or more resistors to get a resultant value which corresponds to the value needed for the circuit. When higher values are needed, you will give the resistors in series, and when lower values are needed, you will give the resistors in parallel. Having gone through the topic list to be learned for Amateur Radio Examination ASOC in India, we will start refreshing our memories by revising mostly what we learned at school. Please note that this is for the pleasure of learning and not an official training program. We often call ourselves as lifelong learners. Electronics uses active and passive components to control the movement of electrons. Electrons are tiny subatomic particles seen in all matter outside the nucleus of atoms. Continuous movement of electrons in a material constitutes an electric current. When there is no continuous movement of electrons, but there is an excess or deficit of electrons in a material causing it to be electrically charged, we call it static electricity. Materials with free valence electrons in outer shells act as conductors, while those without free valence electrons are insulators which do not conduct electricity. In general, metals like copper, aluminum and silver are good conductors of electricity, while ceramic and plastic do not conduct electricity well and act as insulators. Though an electric current is due to flow of electrons, by convention it is considered to flow from the positive pole of the battery to the negative pole as shown in the animation. Actual flow of electrons in the circuit will be in the opposite direction. The current flowing through a circuit is measured in amperes or milliamperes. Potential difference across the poles of a battery or across a device is measured in volts. The potential difference across the terminals of a power supply is known as its voltage. The force which causes movement of electrons producing an electric current is known as electromotive force. Passive devices are electronic components like resistors, inductors, transformers and capacitors. They do not alter the waveform of an alternating current applied to them and hence cannot be used to amplify or rectify currents. Active devices are vacuum tubes, semiconductor diodes and transistors, or a combination of active devices and passive devices like integrated circuits. They can change the waveform of an alternating current applied to them and hence can be used for amplification and rectification. Rectification is the process of converting alternating current to direct current flowing only in one direction, while alternating currents change direction with a periodicity. Resistors are passive electronic devices which resist the flow of currents through them. Resistance is measured in ohms and sometimes mentioned in higher units like kilo ohms, meaning 1000 ohms, and mega ohms, meaning 1 million ohms. Resistors can be used to limit current in a circuit, as while using a resistor to avoid excessive flow of current through a light emitting diode or LED. They can also be used to provide a voltage using a voltage divider circuit of 2 or more resistors, as in case of providing a bias for the base terminal of a transistor. Transistors are semiconductor devices with base emitter and collector terminals widely used in electronic circuits. Two important types of resistors are wire-wound resistors and carbon resistors. The resistors illustrated earlier are carbon film resistors, the resistance value of which depend on the amount of carbon present in them. Wire-wound resistors can be made of nichrome wire and usually have higher power rating. Variable wire-wound resistors have been conventionally used in rheostats, which are variable resistors with a sliding contact. Variable resistors are also called potentiometers. They have 3 terminals unlike the usual resistors which have only 2 terminals. Central terminal provides the variable resistance with respect to the other terminals. Potentiometers can have a turning knob to alter the resistance value in the circuit and are widely used as volume controls in radios and amplifiers. A preset potentiometer is one in which the resistance value can be changed using a screw-like mechanism and set at the value until it is altered later if needed. Power dissipation capacity of the resistor usually depends on its physical size and can be rated at 0.25 watt, 0.5 watt, 1 watt, etc. Now I am demonstrating the change of resistance, continuous change, as the potentiometer screw is being turned. Just like tuning a radio. The value of the resistor is indicated on the resistor with a color code. The resistors shown here have a 4-band color code, which is the most common one in use. First 2 bands indicate the resistance value, which has to be multiplied by the code on the 3rd band. 4th band indicates the tolerance. All the resistors shown here have a golden band for the tolerance, indicating 5% variation above or below the coded value. If there is no tolerance band, the tolerance is presumed to be 20%. Color code values are as follows: black 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, grey 8, white 9. Golden color is for 5% tolerance, while silver color is for 10% tolerance. As mentioned above, if there is no tolerance band, it implies 20% tolerance. 3rd band is used as a multiplier for the first 2 bands. Multiplication is by 10 to the power of the 3rd band color code. Multiply by 1 if it is black, by 10 if it is brown, and by 100 if it is red, etc. This is a symbol of a resistor used in circuits and indicated by the letter R. Resistors can be connected in parallel or series. When the resistors are connected in series, the total value is the sum of the individual values. When they are connected in parallel, it is a complex calculation as shown here. Checking the total value of resistors connected in series is rather simple. You just have to add the total values of each resistor and you get the final value. But it is not that simple when you connect resistors in parallel. You have to take the inverse value of each resistor, sum them up, and finally get the inverse of the sum to get the final value of resistors connected in parallel. To simplify things in the demo, we will take three 10K resistors. 10K resistor has a brown band in the beginning representing a color code of 1, followed by a black band representing 0, and then an orange band representing the multiplier of 1000 or 10 to the power of 3. So the value will be 10 into 1000 is equal to 10,000 or 10 kilo ohms. Single 10K resistor on breadboard measures 9.82K with golden tolerance band of 5%. Selector at 20K position. Three 10K resistors on breadboard measures 29.6K with golden tolerance band of 5%. Selector at 200K position. Two 10K resistors in parallel on breadboard measures 4.91K, about half, with golden tolerance band of 5%. Selector at 20K position. Three 10K resistors on breadboard in parallel measures 3.2K, about 1/3, with golden tolerance band of 5%. Selector at 20K position. Same value of resistors were used for simplifying the calculations so that it is easy to check by mental calculation. If different values are used, it will be more difficult to calculate like that. Next important passive electronic component after resistor is the capacitor, which can be used to store electrical energy. There are various types of capacitors available in the market, like electrolytic capacitors with a thin layer of electrolyte connected to metal plates, capacitors using paper as dielectric, capacitors with air as dielectric, and ceramic capacitors. Each one is for a different purpose. There are also capacitors in which the capacitance can be varied, known as variable capacitors, often used in tuning resonance circuits. Capacitance is measured in farads, microfarads, nanofarads, or picofarads, depending on the value from higher to lower. High capacitance in circuits for smoothing out ripples in rectified direct current uses several thousand microfarads. Farad being a large unit is seldom used. A typical tuning capacitor in radios may be rated at 500 picofarads, 500 pf. A capacitor is said to have a capacitance of 1 farad if it can store 1 coulomb charge at a potential difference of 1 volt. There are few symbols associated with capacitors. This symbol 2 lines is for a fixed value capacitor, like the ones which I have shown. And this is a polarized capacitor. Electrolytic capacitors have positive and negative poles which are to be connected according to that in the circuit, while ceramic and paper capacitors or air capacitors do not need that. And this is the symbol for a variable capacitance, mostly used in tuning, and sometimes there are presets also. You can use a screw to change the capacitance and then fix it like that. It will not be a tuning knob in some of the preset capacitors. They are usually smaller ones also. You may need to combine two capacitors to increase the capacity. When two capacitors are connected in parallel, the total capacity will be sum of the two capacities. Suppose you combine two 1000 microfarad capacitors in parallel, then it will be acting as a 2000 microfarad capacitor. If you combine in series, the capacity will be lower. While capacitors are combined in parallel to obtain higher value of capacitance as in filtering circuits, series connection is to achieve higher working voltage, though the resultant capacitance will be lower. As in the case of resistors, inverse of the capacitances have to be added and the inverse of the sum obtained to get the resultant value of capacitance. The equivalent capacitance will be less than that of any of its components. These are a few electrolytic capacitors which I fished out from my recycle bin or rather electronic junk box recently. The focus will be on this bigger one. You can see that this has a higher capacity rated at 1000 microfarad. The working voltage is given as 50 volts. And you can see that there is a minus sign here. That means this particular lead is for negative electrode and this one is positive. Another way of finding out is by the usual notation. The positive one will be longer. This is followed for most of the electronic components like diodes. Filter capacitors are used to smooth out the ripples in rectified DC. That is, when you use a diode, rectifier diode to rectify AC to DC, there will be ripples. Ripples in a rectified current can be smoothened by using high value capacitors like this. This is 1000 microfarad. You can use 2000 also, and multiple capacitors in parallel as well to smooth out the ripples in rectified current. Electrolytic capacitors have one plate as an aluminum or tantalum plate with an oxide dielectric layer. Second plate for an electrolytic capacitor is a thin layer of electrolyte which is connected to the circuit by another foil plate. Though electrolytic capacitors have very high capacitance, they have poor tolerance, high instability, gradual loss of capacitance, especially with high ambient temperature, and high leakage current. Electrolyte leakage from poor quality capacitors could damage the printed circuit board as well. There could be self-degradation if left unused for a long period, like a year, and might lead to short circuit when full power is applied. At high strengths of electric field above the nominal working voltage of the capacitor, the dielectric separating the two plates of the capacitor might become conductive. This is known as breakdown voltage of the capacitor. Maximum energy which can be stored in a capacitor is limited by the breakdown voltage. The air gap between plates of capacitors used in high voltage vacuum tube circuits need higher spacing to prevent arcing. Capacitors with mica as dielectric between the capacitor plates have much higher breakdown voltages than air capacitors. Ratings of capacitors in general applications may range from few volts to kilovolts. Dielectric has to be thicker for higher voltage rated capacitors, making them larger. When a capacitor is connected to a circuit with direct current supply, it will allow current to flow till it becomes fully charged, usually a fraction of a second, depending on the capacity of the capacitor. Once fully charged, dielectric does not allow further flow of current through the circuit. Initial flow of current is only to charge the capacitor plates and not through the dielectric when the voltage applied is below the breakdown voltage. Beyond the breakdown voltage, the capacitor gets damaged and may produce short circuit. When an alternating current is applied to a capacitor, as it changes polarity with a fixed frequency, the capacitor keeps on charging and discharging. Here the current continues to flow through the circuit, though electrons do not cross the dielectric material of the capacitor. In effect, a capacitor blocks DC while it allows AC to flow. Higher area of the capacitor plates increases the capacitance. In other words, capacitance is directly proportional to the area of plates. Relation between the spacing and capacitance is the other way around. Closer the plates, higher the capacity of the plates to hold charges, because electrostatic pull on the electrons collected at the negative side of the voltage source will be more. So, capacitance is inversely proportional to the spacing between the plates. But too close plates will cause arcing at high voltages. Dielectric constant of the material between the plates is also important. Compared to vacuum, air has a dielectric constant of 1.0006, while mica has a dielectric constant ranging from 5 to 9. Higher the dielectric constant, higher the capacitance. This picture illustrates different types of capacitors. From left to right, they are multi-layer ceramic capacitor, ceramic disc, multi-layer polyester film capacitor, tubular ceramic capacitor, polystyrene capacitor, metallized polyester film capacitor, and aluminum electrolytic capacitor. We discussed about conductors and insulators earlier. There is another group known as semiconductors like germanium and silicon, which are bad conductors of electricity in their natural form. If some impurities like boron or antimony are added in minute quantities to these, they can have either an increase in free electrons or a deficiency of electrons. Then they become semiconductors. The process of adding impurities is known as doping. When there is a deficit of electron, it is called a p-type semiconductor. They have positively charged holes as charge carriers. N-type semiconductors, on the other hand, have excess electrons as charge carriers. Silicon has 4 electrons in the outermost shell. When it is doped with boron, having only 3 electrons in outer shell, it becomes a p-type semiconductor with deficit of electrons or holes. Doping with antimony, which has 5 electrons in the outer shell, makes it an N-type semiconductor with an excess of electrons. P-N junction is constituted by a combination of p-type and n-type semiconductors in a diode. Current flows across the junction only when the positive pole of the battery or voltage source is connected to the p-type semiconductor. This situation is known as forward bias. Positively charged holes are repelled by the positive terminal of the battery. Similarly, electrons are repelled by the negative terminal of the battery. They cross the junction and combine with each other. For this crossing to occur, there should be at least 0.7 volt for silicon junctions and 0.3 volt for germanium junctions. At lower voltages, there is a depletion zone of carriers at the junction. This causes a current to flow across the PN junction when it is forward biased. In the reverse bias situation, no current flows across the PN junction. That is how a semiconductor diode functions as a rectifier, converting alternate current into pulsating direct current as it cuts off one half of the AC. A diode is composed of a PN junction with P-type semiconductor on one side and N-type semiconductor on the other side. That is the PN junction. Then we have to know that when it is forward biased, there will be a depletion zone here where the current carriers will be minimal. And forward bias means P-type is anode that is connected to the positive pole of the battery, and cathode or the N-type is connected to the negative pole of the battery. This is the electronic symbol corresponding to the diode. Then this is the blown out picture of the diode. You can see that there is a ring at one end, or either a marker, which you can see here also, but this is a real diode. The marker is very tiny. If you are careful, you can see, or with when you see it directly, you can see very well. This is a rectifier diode, and this will be the cathode, and this will be the anode of the diode. So this basic information is needed. And when a diode is forward biased, these are silicon diodes. When silicon diodes are forward biased, there will be a voltage across, that is 0.7 volt. Usually for silicon diode it will be 0.7 volt, and for germanium diodes, which are seldom seen nowadays, it will be 0.3 volts. So this is what we are going to measure using a multimeter in the mode for diode testing mode. There is a selector switch which will select for diode testing. We have to know about the concept of peak inverse voltage, that is the maximum voltage which the diode will withstand in reverse bias condition. Usual diodes will withstand about 50 volt in reverse bias condition, but there are high voltage diodes also which can withstand very high voltages. So that is peak inverse voltage. When you apply an alternating current to the diode for rectification, you know that during one half of the alternating current, the diode will be forward biased, and during the other half of the alternating current cycle, it will be reverse biased. So that is where this peak inverse voltage comes in. If the peak inverse voltage is low and you are applying a higher voltage of alternating current to the diode, then it will break down. For testing a diode, you have to choose the selector switch in such a way that it indicates the diode symbol. That is how you test it. And then the black lead is connected to the cathode and the red lead is connected to the anode. Here I am using a yellow cable with crocodile clips on either sides to connect from the red lead to the anode, and you can see the display here 555, that is actually 0.555 volts or 555 millivolts, that is being shown here. Now we will reverse the connection and see. Now the connection of the diode has been reversed, and you can see that what is shown is 1. 1 in this multimeter means it is beyond the range. It is not measuring that. So that is because this is reverse biased now. When the diode is reverse biased, no current flows across the diode till it reaches the breakdown voltage or peak inverse voltage which we discussed in the beginning. Now I am testing another diode of the same type. You can see that there is slight difference in the voltage across the diode in forward bias condition, it is 538 millivolt rather than 555. This was the diode which we tested initially, and this is another diode. There is slight difference. Such variation can occur from device to device. Transistor is a semiconductor device invented by John Bardeen, Walter Brattain, and William Shockley in 1947, and they received the Nobel Prize in Physics for this invention in 1956. It is a device used to amplify and switch electrical signals. Large number of transistors can be included in a single chip known as an integrated circuit, which are the building blocks of modern computers and many other solid-state devices. Most of the transistors are currently made from silicon, while germanium was used earlier. Field effect transistors have only one kind of charge carrier, while bipolar junction transistors may have two kinds of charge carriers. In comparison to vacuum tubes, transistors are much smaller and require less power, often working at much lower voltages. Currently, two basic types of transistors in use are the field effect transistor FET and bipolar junction transistor BJT. Terminals of the FET are named as gate, source and drain. Voltage given to the gate can control the current between source and drain in case of FET. Terminals of BJT are named base, collector and emitter. Current at the base terminal, which flows between the base and emitter, can control or switch a much larger current between the collector and emitter. That is how BJTs are used for amplification and switching. BJTs are generally grouped into two, NPN and PNP, depending on the types of semiconductors in them. N-type semiconductor has excess of electrons, while P-type semiconductor has a deficit of electrons or holes, which are considered as positive charge carriers and hence the name. These two types are made by mixing small amounts of other materials into the silicon chip by a process known as doping. There is difference in the amount of doping between various layers of NPN and PNP transistors. Emitter is heavily doped compared to other two layers. Collector is typically doped 10 times lighter than the base. FET is also sometimes called a unipolar transistor, as they have only a single type of charge carriers. They can be N-channel or P-channel depending on the type of semiconductor used. They are named as field effect transistors as they use an electric field to control the current. Two types of FETs are the junction FET or JFET and metal oxide semiconductor FET or MOSFET. Voltage applied to the gate terminal controls the conductivity between the drain and source. Though Julius Edgar Lilienfeld proposed the concept of a field effect transistor in 1925, a working prototype could not be made then and had to wait for further development of semiconductor technology. Three main types of configurations in which transistors are used are the common emitter, common base and common collector. While two leads each are needed for input and output of an amplifier circuit, the transistor has only three. So one lead has to be common between input and output. The transistor configurations are named after the lead which is common to both input and output in the given configuration. In actual circuits, there will be resistors and capacitors in addition. Radio frequency circuits will have inductors and transformers as well. Values of each component will be calculated according to the purpose of the circuit. In all these configurations, the emitter is forward biased and the collector reverse biased. Most common type is common emitter configuration, in which emitter is grounded, base acts as the input and collector as the output. So the input is given between the base and the emitter, which is grounded. Current gain in this configuration, which is the ratio of collector current to the base current, is known as beta or HFE, which stands for hybrid parameter forward current gain common emitter. Beta is always more than 1. This configuration has medium input and output impedance levels. Both current and voltage gains are medium. There is a 180-degree phase change between input and output, so that output is the inverse of the input. In common base configuration, emitter is the input terminal and collector is the output terminal, while base is the common terminal. This configuration is also known as grounded base configuration. Alpha is the current gain in common base configuration. It is the ratio of collector current to emitter current. Alpha is always less than 1. When there is no AC input, the alpha is known as DC alpha. Low input impedance and high output impedance are features of common base configuration. Voltage gain is high, but current gain and overall power gain is low compared to other configurations. The input and output signals are in phase in common base configuration. Low input impedance can provide a good match to 50 ohms, which may be useful in RF linear amplifiers. Grounding of the base can also reduce unwanted feedback between input and output stages in RF circuits. Base is the input terminal in common collector configuration, also known as grounded collector configuration, and emitter follower. It is called emitter follower because the emitter voltage follows that of the base, though the emitter voltage is lower by an amount equal to the turn-on voltage of the base emitter junction. Here output terminal is the emitter. Gamma is the current gain in common collector circuit. Though the current gain in this configuration is high, voltage gain is unity. Input and output signals are in phase. Emitter follower configuration has high input impedance and low output impedance. High input impedance is useful in preventing loading of the previous stage. Thus, it is an ideal buffer amplifier. Current gain or amplification occurs in transistors between the base and collector currents with common emitter configuration. It is technically termed as HFE, which stands for hybrid parameter forward current gain common emitter. Another term is beta of the transistor. It is measured by dividing the collector current by the base current in a common emitter configuration. Most digital multimeters have an option to check the HFE of transistors. The transistor has to be inserted in the NPN or PNP slots according to the pinout diagram, and the selector knob turned to the HFE option to read the value on the digital display. Here you can see that BC547B, which is an NPN transistor, has been inserted in the socket for NPN transistors, and the selector knob has been turned to HFE on the dial. Digital display shows HFE value is 256, which is the current gain of this device as measured by the digital multimeter. Kirchhoff's circuit laws are two equalities that deal with the current and potential difference or voltage in electrical circuits. Described in 1845 by German physicist Gustav Kirchhoff. Interestingly, this year corresponds to the 200th birth anniversary of Kirchhoff. According to Kirchhoff's current law, total current entering a junction in an electrical circuit is equal to the total current leaving the junction. Kirchhoff's current law is also known as Kirchhoff's first law or junction rule. It is based on the conservation of charge principle, which states that electricity is neither created nor destroyed as it flows through a circuit. Kirchhoff's current law is considered while designing and analyzing circuits, troubleshooting and repairing circuits. If currents entering a node is assigned positive values and that exiting it negative values, according to Kirchhoff's current law, the algebraic sum of all currents entering and exiting the node will be zero. It is the basis of most circuit simulation softwares and is used along with Ohm's law to perform nodal analysis. Nodal analysis, also known as node voltage analysis or branch current method, is a method of determining the potential difference between nodes, which are points where elements or branches connect to an electrical circuit. An important limitation is that it is not applicable in high frequency alternating current circuits. Capacitive coupling of electric field can occur between the wires of a transmission line. Kirchhoff's voltage law, also known as Kirchhoff's second law or Kirchhoff's loop rule, mentions that the sum of all voltages or potential differences around a closed loop is equal to zero. This means that sum of all individual voltage drops in a closed circuit will be equal to the voltage applied or supply voltage. In such a loop, the current path does not encounter a node more than once. Circuits having multiple loops can be analyzed by applying Kirchhoff's voltage law to each of the loops. Kirchhoff's voltage law follows the principle of conservation of energy. The loops can be traced in clockwise or counterclockwise direction.